Okay, let's get started. We'll continue what we covered on Tuesday, which was, if you remember, we covered memory. Actually, I should go to the next slide. Today we're going to talk about computation and memory. But last time we covered major trends affecting main memory, and we talked about several key challenges and solution directions, and we focused mainly on the robustness, reliability, and security challenge. This time, we're going to move to energy and performance in memory computation, which is also a very exciting part of memory. Let me go into the sub-agenda a little bit. So I think of, if you remember from the last lecture, I motivated intelligent memory controllers quite a bit. And the perspective was bottom-up. Basically, the reliability and security issues that we're having at the circuit and device levels were pushing us to make the memory controller more intelligent. Like to solve the row hammer problem, you need a slightly intelligent memory controller. To solve other problems, you may, to eliminate refreshes, for example, retention time issues, you want to have an intelligent memory controller that continuously profiles the memory and figures out the retention time of different cells and adapts the refresh rate accordingly. So that's one motivation for having intelligent memory controllers. That's the bottom-up motivation. I will today start with the top-down motivation. There's a huge push or pull from the systems and applications that basically wants a more intelligent memory controllers so that they can offload some of the work to intelligent memory. So I'll motivate from that perspective. And hopefully you will see that we're sandwiched in between. The circuits are pushing us to have intelligent memory controllers today. The applications and systems are pulling us to have more intelligent memory controllers today. That's why I believe it's time for doing more computation inside the memory controller. And now the question is, where is the memory controller? Where is the computation? And that's a large design space that we're going to cover. So we're going to talk about two directions. One is putting the intelligence into the memory chips, but not too much intelligence in the sense that if you put too much computation inside the memory chip is not really designed for that. It has a different process technology. So that may not be viable, but so we're going to look at minimally changing memory chips to do computation that they're really good at doing. And then we're going to talk about more general purpose computation, 3D stacked memory. And then hopefully we'll get to some adoption issues in processing in memory, because this is really changing the paradigm with which we do computation. We normally don't think about memory elements as being active doing computation. So how do we get this to be adopted? So let me talk about the pull that's coming from the systems and application side. Basically, there are three major trends in the system side that is really pulling us to do something about memory. Data access is a major bottleneck. Applications are increasingly hungry, and I give you some examples about that. I'm going to give you more examples. Energy consumption is a key limiter. I already said that, and the memory is consuming a good chunk of that energy consumption. And data movement energy dominates compute energy today. And we're going to look into that a little bit more. This is especially true for off-chip to on-chip movement today. So the observation and opportunity is that the high latency and the high energy that we have is caused by data movement. A lot of it is caused by data movement. We have long energy-hungry interconnects, especially between the computation units and memory. We have energy-hungry electrical interfaces, and we move large amounts of data because the applications need that data to do the computations with. So the opportunity is we want to minimize the data movement by performing computation directly where the data resides or near where the data resides. This is called processing in memory. I'm going to use processing in memory or computation in memory as a general term. You can distinguish between where the processing happens. I'm not going to do that in this talk. But I'm going to use these terms interchangeably. So you can think of in-memory computational processing or near data processing. I'm going to use that interchangeably. And the general concept is really applicable to any data storage and movement units. Caches, SSDs, main memory, network controllers. Wherever the data is, you can do computation. So this is a bigger outline. Remember that I told you that we're going to cover 4 key issues in future platforms. We talked about this one. Now we're going to focus especially on energy efficiency, and which requires, in my opinion, memory centricity or data centricity. But this will also touch into low latency, because if you push computation to where the data is, you're not moving the data, which means that you're not exposing the computation units to the latencies that we're exposing them to today. And I'll talk about Maslow again. I'm going to kind of deconstruct what I said. Yesterday we said that we need to start with reliability and security. But actually, if you look at Maslow's terminology, he said that physiological needs are more important than anything else. And energy is a key physiological need. You need to have food to operate, basically. If you don't have energy, maybe you don't really care about reliability and security. Of course, this is one part of it. Take this with a grain of salt. So the key question in my mind is, do we want something like this, maybe beautiful Switzerland or somewhere, or do we want 1940s Pittsburgh? I think we want something sustainable and energy efficient, meaning that I would prefer the first one. The problem is data access is a major performance and energy bottleneck today. But our current design principles cause great energy waste. It essentially goes against this bottleneck. And also great performance loss. And I put this in parentheses because we do a lot to overcome that performance loss. We design a lot of mechanisms into hardware and software to get rid of the performance loss as much as possible. In hardware, for example, we put heavy out-of-order execution, heavy multi-threading, large cache hierarchies, multiple levels of cache hierarchies, many prefetchers. They tolerate some of that performance loss, but they come at the expense of even more energy waste, because all of those components waste a lot of energy. And the problem is we're basically processing data far away from the data. That's why we're having this issue. So if you look at a computing system, this is von Neumann's seminal paper, where he talks about three major units: computation, communication, storage, and memory. And if you look at how we designed the system today, we basically focused a lot on the computing units. Computing units, we're overwhelmingly processor-centric today. And when I talk about the computing unit today, we have accelerators also. It's not just the general purpose processor, but we have many accelerators. They're all part of the computing unit. And we're very much centric over here. Every other, all data is processed in the processor. You do computation only there at great system cost. Everything else is essentially a dumb. They're largely unoptimized, whereas processor is heavily optimized and is considered the master. Yet, we know that memory is the performance bottleneck, and I'll give you a slight history of this. I'll start with this particular term, which you all knows very well, I think. This is actually coined by Dick Seitz. He said that it's really the memory is stupid, and it's a beautiful one-page article by Dick Seitz, which says that Dick Seitz is the chief architect of Alpha 21-64. He basically says in this article, we designed the fastest processor of its time. It's supposed to finish 4 instructions per cycle, but on these important workloads, it finishes 1 instruction every 4 cycles, approximately. Basically, it's operating at 1/16th of its peak bandwidth. Why? It's waiting for data. And he concludes that article beautifully, I think, saying that future processor design should focus only on the memory subsystem. Very strong. Okay, that's 1990s or so. Fast forward about 10 years. This is data from my own PhD thesis. He'll probably remember this slide, presented to him at many points in time. This is basically, what we've done at that time is we've analyzed the workloads that Intel used to design its processors with, and we found out that most of the time on these workloads, the processor is waiting for memory. This red part is waiting for memory. Okay, if you don't believe this data, fast forward 10 more years, and this is the paper if you're really interested, my first paper in my PhD. If you don't believe that, fast forward 10 more years. This is data from Google. This is a beautiful ISCA 2015 paper where they analyze what they claim to be all of their data center workloads, and they basically find the same thing. In their data center workloads, the processor is most of the time waiting for memory. It's only this green part where the processor is actually finishing instructions, which is about 10 to 20% of the execution time. So we're designing these processors. They become very high performance, but most of the time, they're just waiting for data to come back from memory. The performance has improved because we're trying to tolerate those latencies, but still we're bottlenecked by memory. And if you're really interested, Google has a lot of analysis in their paper. It's a beautiful paper also. Okay, so essentially, this happens because we're processor-centric. We have to move the data all the way into the processor to process it. But this comes at a cost. Essentially, we have a grossly imbalanced system. Because we do processing in only one place, processors or the accelerators, and because everything else just stores and moves data, data moves a lot. And applications need a lot of data movement. And this is energy inefficient. I'll give you more examples of this. This leads to low performance. Processor waits most of the time. And this is complex because we actually need to have all the mechanisms to move the data. And we add even more complexity to tolerate this. The processor becomes overly complex and bloated. That's true for the accelerators today. If you look at GPUs, they're very complex actually. Why? Because they need to tolerate data access from memory. We design all these complex hierarchies, cache hierarchies, prefetching hierarchies, multi-threading, large wide vector units to tolerate memory access. And this makes everything even more energy inefficient. And this leads to performance loss because you have to go through these hierarchies and it becomes more complex. So as a result, you get back to the picture that I showed you 2 days ago. This is my cartoonish picture. If you look at it, most of the system is dedicated to storing and moving data. Computation is a very little part of the system, even though this is called a computing system. Okay, let's take the energy perspective. I've given you the performance perspective. Let's take a look at the energy perspective. If you look at the energy perspective, this is a slide that I borrowed from Bill Daly that looks at the cost of doing different operations in the system. And you can argue with all of these numbers because these are old. You could optimize these numbers. But let's focus on this thing over here. This is a 64-bit double precision floating point operation. It takes about 20 picojoules. A DRAM read or write access, it's about 16 nanojoules. Now if you let me, I'll take the liberty of increasing that 800x to 1000x. Essentially, a DRAM access is 3 orders of magnitude energy inefficient compared to a complex floating point operation. Now this didn't always used to be the case. If you go back to 70 years ago, when von Neumann wrote that seminal paper, and if you try to figure out what these values could be at that time, this was about 2 orders of magnitude worse than a memory access at that time. So over the course of 70 years, this has scaled really well. We were able to reduce the energy of computation really well because of mainly technology scaling. But because the interconnects did not scale very well, and the DRAM technology did not scale very well, this stayed almost constant, if you will, although there are improvements there. As a result, we moved from 2 orders of magnitude, computation being 2 orders of magnitude more expensive, to memory being 3 orders of magnitude more expensive. That's 5 orders of magnitude. But we're still designing systems such that processor is the master. Okay, so if you don't believe that 3 orders of magnitude, there are more realistic numbers, which shows you essentially memory access is about 2 orders of magnitude more expensive than an add operation. And that's a more optimized system. Actually, SOCs are some of the most optimized systems that we have today in terms of energy efficiency. And this number comes from an SOC. Okay, as I mentioned earlier, we did a study with Google. We analyzed the key workloads that we believe, the key workloads. I'm going to go into this more detail later on. And we found out that more than 60% of the entire system energy in these key workloads is actually spent on data movement across the memory hierarchy. Okay, we're going to look at optimizing that later. Essentially, if you want to optimize for energy, we do not want to move data. And to be able to do that, I believe we need a paradigm shift to enable computation with minimal data movements and to compute where it makes sense, as opposed to where the processor is in only one place, which means that where the data resides, or while the data is moving. We need to make computing architectures more data-centric. So our goal is to enable this. Of course, as I mentioned earlier, you could do this in many places. You could do this computation in the storage unit, you could do the computation in the controllers, you could do the computation in the network. We're going to focus on memory. I think memory is a little bit harder because the interfaces in memory are not so flexible today. But you can imagine this being applicable to storage also. So basically, if you want a memory that could store large amounts of data, this already happens. We have in-memory databases today, in-memory graph processing today. But we don't do the computations there. We bring the data all the way to the processor core. But what we would like to do is to store the data and to be able to query the data. Memory sends messages to, the processor sends messages to memory, and the memory responds to that query by, for example, searching for something inside the database and gives the results back. Today we don't have the interfaces for this. There are many questions over here. One is, how do we design the compute-capable memory and the controllers? How do we design the processor chip and the in-memory units? How do we design the software and the hardware interfaces? Today we don't have the software or hardware interfaces to be able to do that, although we could get there slowly. How do we design the system software and the languages and the algorithms on top of that? Because once you have computation capability over here, your algorithm may be completely different than today. So essentially what we're going to look at is an across-the-stack problem. You could design the devices to do computation differently from today, as we will see. And once you design the devices differently, you need to design the algorithms also differently. And you need to design across the stack over here. So it's a fascinating area, but it's not easy to make this happen, at least in the full scale. So we're going to talk about adoption issues later on. So as I mentioned earlier, I'll spend a little bit of time over here in terms of history. This is not a new idea. processing in memory has been posed as an idea for a long time. In fact, earlier analog computers, you could consider them as processing in memory. But the first time, the first paper that I know of in this area is by Harold Stone, who was at Stanford when he did the work. Later he moved to IBM. He wrote a paper called, entitled A Logic and Memory Computer in IEEE Transactions on Computers in 1970. Since then, 1970, 80, 90, 2000, there are a lot of papers in this area. But I believe today is the right time to look at it because we have a huge push from technology that never existed before. And that's exactly what we covered in the previous lecture. DRAM scaling, the main memory technology that we use to build main memories with is threatened. We have all kinds of reliability and robustness and security problems. As a result, industry is open to new memory architectures today, a lot more than before. In fact, as I mentioned, if you actually went to these major memory manufacturers 10 years ago and said, I want error correcting codes in your memory chip, give me 10% of your area, they would kick you out of the room probably. Today, they already have error correcting codes inside the memory chip because they don't know how to deal with some of the reliability issues that they have. So there are other things that we're going to look at. You have logic memory controllers underneath the memory stacks. So these are new architectures that we're going to look at. And there's also experimental chips that people have designed where you could do very limited computation inside the row buffer. You may know of some of these. And there's also a huge pull from systems and applications that we discussed. Data access is a major bottleneck. Systems are energy limited. And data movement is much more energy hungry than computation. As a result, applications are pulling us to actually do something different in terms of how we treat memory versus compute. Okay, so given that, let's talk about how we actually do the computation or processing in memory. In the past, a lot of the works actually look at putting a processing unit inside the DRAM chip. I think that's going to be very hard to do because it's not easy. If you want to put a very powerful processor inside the DRAM chip, the DRAM process doesn't go well with putting a very powerful and not so leaky processor inside. So you usually cannot clock those processors really fast because DRAM process is really designed for the capacitor, minimizing the size of that capacitor. We're not going to look at that solution direction, although part of that solution direction could be interesting if you want to minimize the cost. We're going to look at two different directions. One is how do we change the memory chips minimally such that we can actually speed up some functions that these memory chips could be very good at speeding up. So very simple accelerations. And the other is if you already have 3D stacked memory where we have a logic layer underneath the memory layers, and if you can put computation in the logic layer, that could be relatively fast. What do we do over there? Okay, let's start with the first one over here, minimally changing memory chips. So the realization here is that DRAM or any kind of memory has great capability to perform bulk data movement and computation with relatively small changes. You can exploit the internal connectivity to move data, and you can exploit analog computation capability. I'll give you examples from DRAM over here, but there are examples from page change memory and STT-MRAM and memristors, RRAM, where people have found you could actually do simple computations inside memory chips. Okay. So we're going to start with, not even computation, I'm going to cheat. I'm going to start with some data copy and initialization, which is not computation, but this is something that actually moves a lot of data also in the system. So what is data copy and initialization? Essentially, you copy one page to another page, or you initialize one page with all zeros, for example. If you're initializing a huge database, it takes a long time today to write zeros to memory. And this is actually used in many, many applications, as you might imagine over here. In fact, in this paper that I mentioned earlier, that Google wrote in ISCA 2015, they said only two system calls, memmove and memcopy, consume about 5% of the cycles in all of their data center workloads. And this is not all of the data copy and initialization. This is data copy and initialization that's initiated by just these two system calls. Okay, so how do we do bulk data copy today? If you want to copy the source page to this destination page, let's say a 4 kilobyte page, we have to go through the processor today. We bring the source page byte by byte all the way into the L1 cache. We bring the destination page byte by byte all the way into the L1 cache. We do the copy and we write back the destination back into the memory. So this is high latency because you do many trips from memory. This is high bandwidth utilization on perhaps the most important bandwidth constraint part of the system. This causes cache pollution, but you could eliminate that cache pollution because you could actually set this copy up through the DMA engine with some overhead. And you cause unwanted data movement. If you're not going to use the destination page or the source page, you basically bring all of them into the cache. So if you actually do this copy, 4 kilobyte page copy through the direct memory access engine without even touching the cache hierarchy, it takes about 1,000 nanoseconds and 3.6 microjoules today with some technology assumptions in DDR3 technology. Now, wouldn't it be nice if we had the option to tell the memory controller, memory, please copy the source page to this destination page and don't bother anything else in the system. Now, if you do this, this is low latency because we're going to exploit internal connectivity here, and we're not going to disturb the large interconnects that we have over here. It's going to be low bandwidth utilization because we're not going to move data here. It's going to cause no cache pollution, but you could eliminate that today also. And we will have no unwanted data movement because we're not moving any data out of memory. I'm going to show you a mechanism that in the best case takes 1,046 nanoseconds to 90 nanoseconds. You could actually optimize it to 70 nanoseconds. And 3.6 microjoules to 0.04 microjoules. Let's take a look at that mechanism. It's very simple actually. Remember this picture, memory consists of rows. This is actually one subarray of memory. And rows are connected to a row buffer, sense amplifiers, through the bitwise, if you remember. Now, what we're going to do is if you want to copy a source row to a destination row, and these two rows are in the same subarray, we're going to do 2 consecutive activates, and that's it. We first activate the source row, which brings the data into the row buffer. Now the row buffer stores the data in a very amplified fashion. It's very strong. In the next step, we want to copy the data to the destination row, so we activate the destination row, which implicitly deactivates the source row. And this activation causes the sense amplifiers to drive the data that they have stored into the cells in the row. And that's it. Basically, you accomplish a copy by doing activate to the source row and an activate to the destination row. And this uses the row buffer as an intermediate location to do the copy. And this is negligible hardware cost. It's actually very, very little hardware cost. It's not allowed in today's DRAM chips, but there's no reason it cannot be allowed with very little changes. And this leads to an 11x latency reduction and a 74x memory energy reduction. Now this works if the source and destination are in the same subarray. What if they're in different banks in the memory chip? Again, the infrastructure exists to move the data from one bank to another bank through the shared internal bus in the chip. You basically set the source bank to read mode and the destination bank to write mode through memory controller changes. And then you could pipeline the data movement through the shared internal bus. And you could move arbitrary amounts of data. Of course, the benefit now here reduces because you're using the internal interconnect. It's still better than going through the interconnect between the cluster and the memory. But it's not as high as the 11x reduction. Now we get 2x latency reduction and 3x energy reduction. So you can generalize this mechanism to do all kinds of copies within the chip, which I'm not going to go into detail. The difficult part is doing the copies across different subarrays that belong to the same bank because there is no direct connectivity between them. But we have another proposal that actually increases the connectivity between the subarrays. Okay, so all of this combined gives you about 0.01% area cost in the DRAM chip, very little. And in the best case, you can get significant savings. Of course, this best case you can achieve only if the source and destination pages are in the same subarray, which means that whenever you're doing that copy, if your system software is intelligent and aware of the topology of DRAM, it can allocate the destination page to the same subarray as the source page, and it can exploit the maximal benefits. So if you really want to exploit the maximal benefits, your software, system software, and applications maybe need to be aware of the topology of DRAM and the capabilities of DRAM, even in this very simple case of doing copy. And initialization is a very special case of copy, actually. If you want to initialize a row to all zeros and initialize in your entire memory to all zeros, you basically write zeros to one row and then copy that row to your entire, all of the memory rows. Okay, I'm not going to go into more detail in this, but this leads to corresponding benefits in applications that do copy and initialization. Yes?
What's the software interface like?
So you can have an instruction that's very similar to a map set instruction. In fact, if you know repeat move S in x86, that's essentially doing a copy from a memory location to another memory location and it's repeating that. So the interface for this already exists actually in processors, in many processors. Okay, so similarly, we can actually do in-memory and or not, and I'm going to give you how we do it at low cost by using the analog computation capability in DRAM. But again, as I said, DRAM is just the example that I'm using. This is true for other technologies also. The key idea is activating multiple rows performs computation. I'm going to give you this example in a little bit. And it leads to significant performance and energy improvements. But before I move on, I should say DRAM is not the best technology for this. New memory technologies enable even more opportunities like memristor, resistor RAM, STT-M RAM, phase change memory. DRAM is fundamentally not good in the sense that you have to move, whenever you read a row, you destroy the data, which means that you need to move the data just a little bit somewhere first to do operations on it. Whereas in these technologies, you can do truly in-place computation because whenever you read the data, you're not actually destroying the data. So I think there's even more potential going forward, and there are very interesting works related to this that I'm not going to cover. Let's take a look at the DRAM. How do you do bitwise AND and bitwise OR in DRAM? This is 3 rows in DRAM. I'm going to show you only one cell, but you can imagine that this is actually span across the entire row. So this is 8 kilobytes, 8 kilobytes, 8 kilobytes, let's say. If you actually had the primitive to concurrently activate these 3 rows, in an ideal circuit, what you would get is, if you activate them concurrently, all of them get connected to the bit line. And if at least 2 of them are 2 of these cells are discharged, you get the discharge state at the end. If at least 2 of them are charged, you get the charge state at the end. So because of charge sharing, activating multiple rows lead to computation across those rows. So in this case, if you essentially what I described to you is a majority function. Right? It's a bitwise majority. If at least 2 of the cells are charged, you get the charge state. If at least 2 of them are discharged, you get the discharge state. Now we have bitwise majority. So you can do block bitwise majority in DRAM, which is great. But if you actually rewrite this Boolean equation and control one of the rows, let's say C, if you set it to 1, you get the OR of A and B. If you set it to 0, you get the AND of A and B. Now you have bitwise AND and bitwise NOT, which is good. And you can actually, this is a software interface. You have the question about software interface. If you actually want to expose software, you can have a bulk AND operation. And the semantics is to perform bitwise AND of 2 rows, A and B, and store the results into row C. So the way we implement it is we actually have some reserved rows that are reserved to 0 and reserved to 1. And we don't allow triple row activation inside the entire DRAM subarray because that would be very complex. You need to have 3 row decoders in the entire subarray, which is expensive. So we actually have 3 designated rows where we could do triple activation. If you want to do triple activation, you need to move the data from the row that you want, the source rows into the designated rows. So how do you move the data? You basically use the primitive that I described, row clone. Right? You row clone one of the sources to one of the designated rows. You row clone the other source to the designated rows. And because we are doing an AND, we row clone the reserved 0 row into the designated rows. After that, you triple activate, which performs the AND, bulk AND, and then you move the result into the destination row by row clone. So by combining these primitives, you could actually do operations completely inside the DRAM subarray. Okay, so we're missing. We have yes.
Freddy, so you mentioned that this is not allowed in current memory. Why is that? I mean, is it would be more prone to errors? Is there a fundamental technological reason for that? Or
so row clone is not allowed because you don't have the DRAM standard doesn't allow you to do 2 consecutive activates. Basically, you have to.
Is there a reason?
Technological
reason for
There's no technological reason. No, actually, we talk a lot with memory companies. The cloning operation is very, very easy to add to memory. This bulk, the triple row activation, is not done because the circuit is not designed to enable triple row activation. You need additional hardware for this one. So we have now AND and OR, but this is not functionally complete. So if you want to actually perform any operation, you want to be functionally complete. What's missing is NOT. So we wanted to add NOT into the system. This is a little bit more expensive. Basically, you want to have the complement of a cell. This already exists actually. Whenever you activate a cell, the bit line bar, the other side of the sense amplifier stores the complement of the value. But it's not connected anywhere. So the idea over here is very simple. We want to feed the negated value or complement in the sense amplifier to a special row. This adds a special row in the DRAM subarray. It's a little bit more overhead. It's about 1% area overhead in DRAM, but buys you a functionally complete DRAM where you can do block bitwise operations. And if you actually are able to transform your algorithms, you could do anything inside DRAM. Maybe not everything will be efficient, but some things will be efficient as we will discuss. So this is performance. I'll very quickly go over this. This is the throughput that you get if you actually do these operations. We call this mechanism ambit. This is Vivek Seshadri's thesis. He's at Microsoft Research in India right now. Basically, if you do this, you get significantly higher throughput than existing CPU and GPU systems over here. basically you get, within a single DRAM module, you get on 2 tera-ops per second over here. CPU and GPU are over here. Of course, if you actually increase the GPU capability, you can get more, but now you're not bottlenecked by data movement in the GPU potential. Okay, so in terms of performance, we get significant benefits, but yes?
How long do the operands have to be for this to be useful? So in other words, suppose I just wanted a few bits and is it still useful or not?
Yeah, a few bits is not very useful, unless you're doing that a few bits in many different parts of memory. So it could be useful depending on how many a few bits, but if you're just doing it for a few bits, you're not very efficient. So you need to do masking operations to just to operate on those bits also.
So, you know, if you draw an analogy with vector processing, we talk about the vector half-length.
Yes.
Right, which is how big does the vector have to be for vector processing to actually make
sense? Yeah. So
you have an estimate?
I don't have a very good answer because we didn't really go through those models over here. But it's very useful if you're operating on the entire DRAM row. That's 8 kilobytes. But I didn't look at the cutoff. We didn't look at the cutoff point as to where it doesn't make sense. This is very useful where you're doing a lot of block bitwise operations. Okay. So the energy consumption reduces significantly also. This is for NOT. You reduce the DRAM energy by about 60x, and the NOR, and if you compound the operations XOR, XNOR, it's still 25x. Okay, so where is this useful? Where is this most useful potentially? You could transform any algorithm, I believe, to this, but it's most useful if your algorithm is already doing a lot of block bitwise operations. Yes?
Is further scope to improve the triple activate if you don't have to do row cloning, right? Like, why can't we enable that?
Say it again?
Without doing row cloning, why are we not able to do the triple activate? As like row cloning is
yeah, because you need to triple activate arbitrary rows inside a large DRAM suburb, and you need really row decoders for all of them.
Okay.
3 row decoders, and that's very expensive. Whereas if you have a designated area, you don't really need you need a very simple decoder to send the triple activation signal to all those only 3 rows.
But then row cloning is impacting the latency as well.
That's right. Yeah, the trade-off is that you need to move the data, but that's very fast inside DRAM. It's 70 nanoseconds. Okay, so where is this useful? So we looked at some applications. There could be more applications. We're going to look at bitmap indices. A lot of databases actually use bitmap indices. Some folks, Jignesh Patel's group, designed this database bitviewing for essentially doing column scans very efficiently using GPUs. So this actually we can port to our infrastructure and we get good results. I'm going to show you. Microsoft is designed for very similar reasons to take advantage of GPUs and FPGAs, something called bitfunnel, web search algorithms, DNA sequence mapping, which we discussed 2 days ago, is a very good fit for this. And I believe there are other fits that we're not going to examine. Let's take a look at bitmap indices. Bitmap indices are essentially used by databases as an alternative to B-tree and variants, and gives you efficient range queries and joins. I'm not going to go into the detail, but essentially you can imagine very large bitmaps. And if you're searching for something, you're doing a lot of AND or maybe NOT operations. And we see that you get significant benefits if you actually port these bitmap indices to be operated on inside the Ambit substrate. This is about 6x reduction in query latency. This is another example. We ported the bitweaving database to Ambit, and for particular queries, you get significant performance improvement. Of course, you need to change your application such that the data layout fits your memory. It doesn't come at 0 cost. You have to really change your application. Yes?
So what about the cache coherence overhead while doing Ambit?
Yeah, so it's taken into account over here. We're going to talk about cache coherence. That's one of the adoption issues. So you need to really ensure that your data is correct. Your CPU is not operating on this data while your memory is operating on that data. But that's an important issue. That's an adoption issue of processing in memory, and that affects your programmability. Okay, so the performance, in this case, basically the programmer, meaning Vivek, hand-coded all of this and ensured that the cache coherence is not a problem. But you get significant performance improvements. It's about 12x performance improvement in the query latency. And we looked at some other workloads, but I'm not going to talk about that. So if you're interested, you can take a look at this paper that was published in Micro 2017. Okay, I'll raise question. Basically, this is one example where we can put functionality in DRAM with very, very little overhead, but we're not putting a general purpose processor, we're putting very specialized functionality. And then it's hopefully buying us significant performance and energy efficiency on workloads that could take advantage of that functionality. Any other questions before I move to 3D stack memory? Okay, I'll move. We don't have a lot of time, so I'd be happy to take questions throughout. So let's switch gears on it. As I said, this is a very interesting direction. Surprisingly, it's a direction that has not been examined a lot in the past.
I think you're underselling the general purpose notion. What you've changed is writing code, doing something in software, by writing logic, doing it at the logic design level. And particularly for database, it seems to me that there's a lot of sophisticated queries that you can introduce that is very general purpose.
Yeah.
But you're no longer programming in some, what we normally think of as programming language. Now you're programming in AND gates and OR gates and that sort of thing.
Exactly. I like to think of it that way also, but it's a very different way of thinking.
Absolutely.
It's essentially a different computation model. I call it
That's
the
right.
bitwise computation model.
But it potentially is no less general.
I agree, but it's not very efficient in everything. But that's true for existing computational models also, so I agree with you. Okay, so as I said, actually there's work that shows that you could do this in phase-change memory and other technologies, and if you're interested, I'd be happy to talk about that. So let me move on to 3D stack memory. So 3D stack memory is an opportunity, in my opinion. This is a memory that has a logic layer underneath memory layers, and these are connected through through-silicon vias, very high bandwidth, low latency connections. And there are other true 3D, more monolithic 3D technologies that are under development that do not use the through-silicon vias. Some of them use carbon nanotubes, for example. They're going to be more further out into the future, but this 3D technology can enable computation very close to memory, maybe not inside the memory layer itself, but inside the logic layer that's very, very close to memory. Inside that logic layer, you can essentially put any computation. So this is actually example technologies that we've looked at in our memory simulator, emulator, that we released to the community. And even at that time, there were many 3D stacked memory technologies. Some of these are already deployed in GPUs. For example, you have high bandwidth memory. It's used in a 2.5D stack manner today, but there's no reason why it cannot be used in 3D stack manner. So when we first started looking at computation inside the logic layer, we had several questions. One is, what is the maximum performance and energy benefits that you could get if you use 3D stack memory as a coarse grained accelerator by essentially having the freedom to change the entire system? If you want to change all of the system, what would you get? Or by performing simple functional floating. I'm going to talk about that. And then we're going to switch to what is the minimal processing and memory support you can provide such that you can take advantage of this logic layer. Clearly, there will be a huge difference between the benefits that we get between them, but this will be more adaptable because we were going to target minimal changes to the system and programming. We're going to keep the sequential execution model, for example. Let's start with the first one because this gives us some potential benefits. So when we first started looking at this, graph processing was a very interesting application for us. I believe graph processing is still very, very interesting, not because of these only, but for example, we talk about genomics. There are many graph-based representations of genomes today because genomes are not static. Whenever you actually sequence new genomes, you can actually represent them using graphs. Okay, so scalable large-scale graph processing is challenging because if you throw cores at the problem, you don't get as much speed up. Why don't you get as much speed up? This is one example from PageRank. There are many graph kernels where you have frequent random memory accesses whenever you're updating data or reading data with very little amount of computation. So this is really exercising the energy and performance bottleneck in memory. You need to, you don't have much locality, and you're doing little amount of computation, so your caches are not useful, and you're really moving data a lot. So this is a system that we designed using 3D stacked logic and memory to essentially not move the data into the cores. We're going to take this as a base. This is the logic layer, and this is the memory layer. Maybe I should switch over here. And if you look at the logic layer, in the logic layer you have what's called these volts. And volts are controllers that control the memory stack, the partition of the memory stack on top of them. and you have a number of them that are partitioned, that partition the logic layer, and they're connected to each other with some network. What we're going to do is not just put a memory controller in the logic layer, but put a very simple in-order core. It's actually general purpose. You can do any kind of computation in it. If you pull out a little bit, this is the 3D stack memory plus logic chip. And if you want to actually scale this, we have many of these interconnected in some manner. In this case, we use a dragonfly network. So what these in-order cores do is they're going to be able to process the data that are on top of them in the memory layers. So we partition the graph on top of these chips and inside the vaults. And whenever you need to operate on a graph node or a location in the graph, you need to actually send the operation to the node. So we're not going to move the data, we're going to send the operations to the node. So this is programmed via remote function calls. It's a message passing machine. So if you know about the old machines, J machine for example, it's very similar to those parallel machines. Except what we're doing is we're using computation inside inside the logic layer. Essentially, we're going to change this to put or get calls. This is a put call where you send the function to the data. And I'm not going to go through this in detail, but you need to ensure that, of course, you need to synchronize at the right moments to make this work. Okay, on top of this, we have prefetching mechanisms because if you actually have these, let me go back over here. You have an in-order core over here, and this in-order core is exposed to a very high amount of memory bandwidth, and it's not able to saturate the memory bandwidth that you have. So we have some prefetching mechanisms to tolerate to exploit the memory bandwidth that the in-order core cannot exploit. Again, I'm not going to go through a lot of detail. It's a large system design. There's a lot of design choices that's made over here that lead to improvements, but that also limit the potential of the system. So the results I'm going to give you are going to be good, but maybe they're not the best. So we compare the system, Tesseract system, to three systems over here. This is the baseline DDR3 system. This is hybrid memory cube with out-of-order cores, 600. This is the memory bandwidth that's exposed to all of the cores. It goes by a 6x between DDR3 and hybrid memory cube. And this is a hybrid memory cube system with in-order cores. We wanted to compare it to this because you cannot put very complicated cores in the logic layer because you have a thermal problem. The heat that's generated by the cores cannot escape. As a result, you're only limited to very simple cores. And we're going to compare these to the Tesseract system, which looks different because you don't have the processor and memory dichotomy in this one. They're bundled together, if you will. But if you look at the bandwidth numbers, the bandwidth that's exposed to the cores over here is about 8 terabytes per second, significantly higher than existing systems. And eventually, the performance improvement is also high. This is average across 5 graph processing algorithms. The details in the paper. You get about 9x performance improvement if you do not do prefetching. But if you add the prefetching mechanisms we described in the paper, you get about 13 to 14x performance improvement. I do not believe this is the best you can get. There are a lot of design choices that you need to make in the system to get even better performance, in my opinion. So we're actually exploiting significant fraction of the 8 terabytes per second memory bandwidth. It's about 2.9 terabytes per second, which means that we're not exploiting all of it. So where are the benefits coming from? Very quickly, there's some analysis in the paper. Some of the benefit is actually coming from exposing more bandwidth, but some of the benefit is coming from actually changing the entire system, including the programming model. And the results are kind of half and half. So here's an example over here. This is a hybrid memory cube system with many cores. If you actually increase the bandwidth magically to 8 terabytes per second over here, you get about 2.3x performance improvement. This is Tesseract with conventional bandwidth, at 640 gigabytes per second. If you actually do processing in memory on top of that, if you actually increase the bandwidth over here, again, you get about 2x performance improvement. So you get 2x from the bandwidth, you get 2x from the programming model. And these are the energy benefits. On average, you get about 8x energy reduction by designing the system. Okay, I've gone through this relatively quickly, but if you're really interested, you should read the paper because there are a lot of design choices in there. Of course, in this case, we've changed a lot in the system to get more than about an order of magnitude performance improvement and an order of magnitude energy improvement. Now the question is, can we actually, what if we don't want to change the entire system? Can we use 3D stacked memory in some other way? So the next thing we looked at was looking at simple functional flooding. I'm going to talk about this paper that I mentioned earlier. Basically, we wanted to look at especially consumer devices because these are devices that are really bottlenecked by energy today. And we wanted to look at state-of-the-art workloads, and we collaborated with Google, and we looked at these workloads, the web browser, machine learning framework, and video playback, encoding and decoding functions. And we first wanted to understand the energy cost of data movement with a lot of experiments on real systems. We found out that more than 60% of the total system energy is spent on data movement in these applications. And to get rid of the data movement, we wanted to look at processing inside the memory, inside the logic layer again, by moving computation close to the data. The challenge in these systems is you have very limited energy and area budget, so what you can put inside the logic layer cannot be very energy hungry. And if you want to look at that, you take a look at the paper for more detail. So our second observation in this work was that a significant fraction of the data movement actually comes from simple functions. Simple functions like data copy. I'm going to give you more examples, like compression and decompression are other examples. And we can design lightweight logic to implement these simple functions in memory. You could have something similar to what I described, very small embedded low power core, in-order core. Or you could have small fixed function accelerators. If your logic layer is especially reconfigurable, you can actually change those accelerators as you execute the code potentially. And we found out that offloading to this processing in memory logic improves energy and performance by about 2x on average in these workloads. So you don't get the 13x benefit. We're doing simple function offloading. So what Amirali did in this work is to go through all of those workloads and figure out which functions would be profitable to offload to the logic layer. And he offloaded them. And the benefit you get is about 2x. We're not changing the system. The programming model is still the same, except you need to synchronize, of course, between the memory and processor. Okay, so I'm going to skip this goals part. I'm going to give you an example workload analysis. I'm going to pick TensorFlow over here, although I think Chrome is very, very interesting, and video is very, very interesting, but everybody's, for some reason, very interested in machine learning, so I'm going to talk about that. So if you look at TensorFlow Mobile, essentially it's a neural, we're going to examine some neural networks that provide some prediction through inference. And we found in our analysis that more than 50% of the inference energy is spent on data movement. And there are two major functions that lead to a significant fraction of that data movement. Essentially packing and unpacking of data and quantization of data. So if you look at these neural networks, whenever you move from layer to layer, you may actually change the data, how the data is organized, and you change the amount of data that you operate on. So we're going to look at these two functions. These two functions are actually very suitable to offload to memory. So what is packing? Packing reorders the elements of matrices to minimize cache misses during matrix multiplication, and this causes significant amount of data movement and energy consumption. But it's a very simple data organization process that requires very simple arithmetic. You basically change how your data is laid out. In quantization, you take a larger granularity data and you basically quantize it to a smaller granularity. And this is one example. You take a 32-bit floating point number, you quantize it into an 8-bit integer. And a lot of machine learning frameworks do that because these are too, first of all, they're unnecessary to operate with and they're too large to operate with. And this consumes a lot of energy and execution time, and the majority of quantization energy comes from data movement. And this is also a simple data conversion operation that requires shift, addition, and multiplication. Now, these are very easy to offload to functional units that are right next to memory. And that's essentially what we did in this work. So I'm going to give you some example results over here. So this is the TensorFlow packing and quantization. If you offload it to a core that's in the logic layer, you essentially improve performance, improve energy by about 2x. If you actually offload it to specialized accelerators for that, you save a little bit more energy because now you're specializing as opposed to using an in-order core. But if you look at the browser, there are significant benefits that you get by offloading compression and decompression to the logic layer. And it turns out these are benefit even more from the accelerators. And in the video playback and capture, there are already hardware accelerators actually on the processor side in video playback and capture. By moving some of those hardware accelerators to the logic layer, you get significant benefits in terms of energy over here. Okay, so the ballpark is about you get 2x energy reduction. And this is also similar, I'm going to skip these animations. The runtime is also similar. Accelerator actually affects the runtime significantly in many of these cases. So if you actually offload these functions to accelerators that are next to memory, you get about 2x performance improvement or execution time reduction. Okay, so if you're interested, you can take a look at this paper. Any questions? I'll keep going then. Okay, so these are some examples. There are actually more examples. GPUs, for example, are processing engines that are very much bottlenecked by main memory bandwidth. So we've been looking at offloading functions to GPUs, smaller GPUs that are in the logic layer. Of course, we cannot put a very, very powerful GPU in the logic layer because the energy consumption is too high. And we're looking at systems that look like this. Then the question is, what do you offload over here? We look at actually programmer transparent offloading mechanisms. So if you look at this paper, it develops a simple compiler mechanisms to offload some thread blocks to GPUs, simpler GPUs that are underneath memory. And because it's completely programmer transparent, the performance improvement that you get is not very high. The performance improvement that you see in this paper is about 30 to 50%. We're going to get back to that. And we're going to look at scheduling techniques, and we're going to look at accelerating pointer chasing also in the logic layer. Pointer chasing is very latency sensitive. So if you actually offload, build an accelerator in the logic layer, you get significant performance improvements. We see significant benefits from linked list acceleration. And we've been looking at Milad actually, who was here, a Yale student. He's looked at improving, putting functionality in the memory controller to reduce the latency of dependent cache misses. Okay. So let's talk about the other direction. What is the minimum processing and memory support we can provide? Even function offloading is not minimal, I would say, because it requires a function to be offloaded. But if you want to be minimal, what can you do? We want minimal changes to system and programming in this case. I'm going to introduce PIM-enabled instructions. The goal is to develop mechanisms to get the most out of the near data processing with minimal cost, minimal change to the system, and no changes to the programming model. So we want to keep the sequential programming model. So there are two key ideas in this work. They're orthogonal. One is to expose each processing in memory operation as a cache-coherent, virtually addressed post-processor instruction called PIM-enabled instruction that operates only on a single cache block. So we're going to restrict the granularity at which we're going to do processing in memory operation, single cache block. So for example, we'll have a PIM-add operation over here. This has no changes to the sequential execution programming model, no changes to virtual memory because the translation happens at the processor side. And everything else, actually, you need to think about virtual memory. I didn't talk about that, but if you're actually executing a function inside the memory, how do you deal with virtual memory, virtual to physical translation? You need actually virtual to physical translation mechanism inside the memory, but this doesn't require that because you do the translation inside the processor before you send the operation to memory. Minimal changes to cache coherence, and there's no need for data mapping actually. Each PIM-enabled instruction is restricted to a single memory module. And the second idea, which is orthogonal, we dynamically decide where to execute the PIM-enabled instruction. It's not always beneficial to execute in memory or the processor. You need to dynamically decide where to execute what. So let's take a look at one example. Again, going back to PageRank, you do this computation. We're going to, if you actually do it this way by pulling the data into the processor, you get 64 bytes inside the host processor. And then when you write the data back, you need to write 64 bytes. So you actually transfer 128 bytes. But if you actually do this PIM add and you decide to send the value to main memory, you just need to send, let's say, an 8-byte value. Which means that you can reduce the bandwidth by about 16x in this particular case. So do we want to always send the value to memory? The idea is basically it's not a good idea. So we looked at graph processing. In this case, if you actually have smaller graphs that fit in your cache, it's better to do these operations in the cache. So if you actually send those operations to memory, you lose performance. But if you gain performance if you're really bottlenecked by your memory. So in this case, you reduce the memory bandwidth because your data sets don't fit into cache. But here, your caches are very effective. If you push the computation to memory, you actually lose performance. So you don't want to do the computation in only one place. You actually want to have a decision mechanism, and this paper introduced a decision mechanism. Okay. So then the key question is, what are the instructions that you want to implement? In my opinion, having a reconfigurable logic layer or configurable logic layer is a good idea because you may want to change the instructions as well. So these are the instructions that we found were interesting for the workloads that we examined. Junman did this work, and these are the instructions that he came up with. For example, more complicated instructions are Euclidean distance instructions. or dot product instructions support vector machines, for example. There are also simpler instructions like 8-byte integer increment. This is of course very application dependent. I think, again, having a reconfigurable logic there is a very good idea. But if you look at all these instructions, they operate only at most on 64 bytes. Because a cache block is mapped to only a single memory module, and we don't want to deal with coherence issues that come about because of due to operating on multiple cache blocks. Okay. So the key to practicality is what I just said. Each PIM-enabled instruction access at most one last level cache block, and actually similar restrictions exist in existing systems like atomic instructions. There are multiple benefits to this. One is easier support for cache coherence clearly, virtual memory also, because you may actually be on the boundary of a page. Each PIM-enabled instruction is bounded to one memory module, so you operate only on that memory module. This is a problem that we didn't talk about, but data mapping is a problem which we will talk about in a little bit. And this actually simplifies locality monitoring. Now you can decide what is the locality that you have on that cache block, where is that cache block, and if it's in memory, you operate in memory, if it's in the cache, you operate in the cache. So what are the benefits that you get? We've looked at 10 data-intensive workloads, including graph processing, in-memory data analytics, machine learning, and data mining. And essentially, we customized the instructions as much as we could in these designs. And these are the benefits that we got. You get about 47% average speed up with the large input data sets. And with the small input data sets, you get about 30% speed up. And the energy reduction is about 25% in a single node. So it's again not 13x. It's not 2x. It's lower than that. But we're changing very little in the system. So I'm going to go through this relatively quickly. With a large input set, you get significant benefits. There's no question. And the difference over here is this is actually if you execute everything in the processing memory, the instructions, or you decide dynamically where to execute, CPU or processing in memory based on where the data is. So that buys you a little bit of performance. And the interesting part is small input data sets. If you send the PIM-enabled instructions always to memory, you actually lose significant performance in all of the almost all of the applications. But if you actually dynamically decide where to execute, you curb all of the performance losses and you actually gain performance slightly. And there are also interesting cases like medium input data sets. It's not clear whether your data set actually fits in the cache or doesn't fit in the cache, or the program changes behavior. That's where the dynamic mechanism to decide where to execute the instruction makes a big difference, as you can see over here. This is the geometric mean performance improvement. And these are the energy results. Again, I'm not going to go into this in detail, but you can take a look at the paper. Overall, with large input data sets, you get significant energy reductions, about 25% over here. Okay, so we've talked about, we could do this analysis for everything, but I'd like to do this for PIM-enabled instructions. The advantage of this is it's one of the simplest and lowest cost approaches to processing in memory. There's no change to the programming model, no change to virtual memory. You don't have a virtual memory requirement on the memory side in terms of translation. And we dynamically decide where to execute instructions. Of course, the disadvantage is you're restricted, basically. You don't take full advantage of processing in memory model. And you have a single cache block restriction. But I believe this is one of the examples of adoption path that we can take to actually get processing in memory adopted. If you actually have these instructions that you could potentially ship to memory, and if your memory is capable of doing it, you ship it, then you actually can achieve better adoption. So similarly, we wanted to actually have programmer transparent mechanisms. I already talked about this. But whenever you go programmer transparent, your performance improvements are commensurately low. And there are other examples over here. Again, Milad's work. And we've been looking at coherence also, but I don't think I have time to talk about that. It's very interesting. How do you actually design efficient coherence mechanisms between the processing in memory engine and the processor? Because if you want to actually operate on some data, you don't want to actually go back to the coherence engines in the processor, because that actually defeats the purpose of doing processing in memory. Right? How do you actually minimize the coherence overheads? Okay, so the challenge and opportunity is we want energy efficiency and high performance, and I think both of them require data centricity today. And we want to minimize the data moment. So let me talk about adoption issues very quickly, and then we'll conclude. So clearly there is an array of things that you can do in memory. I'm not sure if you've covered the entire space, but adoption issues are very important. I believe there are 5 barriers to adoption to processing in memory. One is what functionality do you implement and what applications use that functionality. So it starts really with the software. That's why we've actually been analyzing a lot of software, a lot of workloads, and we're trying to understand what should be shipped and what should not be shipped, and what are the heuristics that we can use, and what are the methodologies that we can use to ship. So we're working on analyzing more than 300 workloads right now. We have this big analysis to understand what should be shipped. I'd be happy to talk about that separately. The second is clearly ease of programming, which is related to functionality. What kind of interfaces do you provide? What kind of compiler and hardware support do you provide? The third is coherence and virtual memory, which we've talked about briefly. And the fourth one is runtime systems for adaptive scheduling. How do you decide where to execute what? A lot of these issues actually arise in any kind of accelerator, but processing in memory maybe exacerbates some of them because of the programming model here. So how do you do the data mapping? I'm going to talk about that in a little bit. How do you ensure access and sharing control? And I think the last one is also very important. How do you design the infrastructures to assess benefits and feasibility? Because it's an adoption path, people need to experiment with different infrastructures to get this model to work. So clearly all of these issues span across the stack. So we've written a long paper that talks about some of these adoption issues. If you're interested, this is as we see what the adoption issues may be with processing in memory. But I'll give you one example. Which operations should be executed in memory versus CPU? This is something we deal with. This is something we didn't talk about as much, but if your data is not mapped nicely, processing in memory could be useless. So if you're adding A to B and storing the results in C, and A is here, B is here, and C is here, it's too bad, right? You need to move the data. You really need mechanisms to map the data locally such that you don't need to move the data off the memory chip. And that's an important problem. You either punt on the programmer, and the programmer does that data mapping, not good, or you design mechanisms to enable this transparently. Then you may lose performance. So that's the trade-off between performance and programmability. Okay, so you tackled this in this paper, but again, the performance benefits are commensurately low because we want to do this data mapping completely transparently to the program. How to schedule code is another issue. This is one example of coherence. So here we examine applications where we partition the application such that part of the application is executing on the CPU, part of the application is shipped at the function level to processing in memory, and they actually share data. Here there's data sharing. One of them updates the data and the other one reads the data. Examples of this are in-memory databases where you do hybrid transactional and analytical processing. Transactions are good fit for CPU. Analytical processing is very good for processing in memory because you actually scan a lot of data, whereas transactional code is better for the CPU because you don't scan a lot of data, but you have a lot of good locality. But now while you're doing the scanning of the data, the CPU may actually update some of that data or vice versa, depending on what you're doing with the scanning. So these applications actually require coherence, and we looked at traditional coherence mechanisms, fine-grained, coarse-grained, and non-cacheable. Please read the paper for more detail. None of them actually give you good performance. In fact, if you have coherence with coarse-grained and non-cacheable, you lose performance in some of these cases when you partition the applications. Whereas the ideal mechanism actually gets you about 50% performance benefit. You may consider 50% not high, but it's actually high for for some of these workloads because these are actually relatively hard to partition. So we have a mechanism that's somewhat transactional, which essentially buys you some of that performance. The idea is it's very similar to transactional memory, but not exactly. You let the memory speculatively execute and essentially record what cache blocks is updated and read. And that's true for the CPU also. At the end of the PIM kernel, which is the end of the function that you've offloaded to memory, you do the check-in to see if the CPU has overlapped, has a data conflict with the code that's executed on the memory side. And by consolidating these checks across large functions, you actually get rid of a lot of the coherence overhead. So the performance improvement that we get with this sort of coherence mechanism is about 30%. Whereas the ideal case where we have no coherence overhead is about 50%. So there's still room for improvement in coherence mechanisms, in my opinion. I don't think this is an easy problem. Okay, how to support virtual memory may be the even harder problem, because if you really want to have virtual memory, and if you want to keep it while we're offloading large chunks of code to main memory, you need to have translation inside the main memory. And this is exacerbated, for example, when you're doing pointer chasing across very large data structures. So every time you have an address, you need to translate the address. So without having a translation engine on the memory side, it's very difficult to translate that address because you don't want to go back to the CPU to get the translation. So how do you design the translation engine on the memory side? This paper proposes a mechanism. I'm not going to go into detail, but this is an area that I don't believe I've seen a lot of good solutions yet. Okay, there are also other issues like how do you design the data structures for processing in memory, which is very interesting because you actually want to parallelize your data structures and processing in memory. If you don't have good data structures, parallel data structures and processing in memory, the comparisons may not be good because today we're able to parallelize the data structures across the CPUs. And if you have serial data structures inside the memory, you actually lose performance. So there's a lot more research to be done in this area also. And infrastructures, I'll very briefly touch upon that. You need good infrastructures to assess benefits. We've developed this DRAM simulator, which we've extended for processing in memory. We'd be happy to share this and support it. We're actually supporting this. A lot of companies and academics are using it. We'd be happy to extend support even more. And we've been also looking at this infrastructure that I mentioned on Tuesday, which is FPGA-based memory testing infrastructure, but you could actually do limited processing and memory evaluations with this FPGA, although it's not perfect. You can still do emulation over here. Okay. So, of course, examining new applications and use cases are important, but I'm going to skip these. This is the bioinformatics work that I earlier mentioned. Okay, so we have a big challenge and opportunity for the future. How do we design fundamentally energy efficient and high-performance computer architectures? I think we need data centricity. And we definitely need intelligent controllers. So let me conclude, and then I'll take more questions. So I think this is one example of a principled system architecture. And the principle is that don't put all of your processing into one place. Distribute your processing across intelligent controllers. And memory is one place, one example of that distributed place where you could do the computation. By putting processing in only one place, you're actually violating a key principle, which you may have seen in classes over here, which is the balanced system design principle. You need to have a balanced system design. But if you're processing in only one place, you have a completely imbalanced system design. And that is affecting performance, that is affecting energy efficiency, because we're not balancing the system. I think a more balanced system is trying to do the operations where the data resides, where it makes sense. And this requires enabling computation capability inside and close to memory, but it's also true that other components need to have that computation capability if you want to have a truly balanced system. So if you have a cache, a very large cache, maybe put some computation capability next to it or inside it with similar principles that we've discussed, such that you don't need to move the data out of that cache, especially if you have very good locality, you get a lot of benefits over there. Storage is another example. I believe this can lead to orders of magnitude improvements. I've given you an example of orders of magnitude. How to achieve that in an easy-to-program fashion is still a research topic. And enable new application and computing platforms, and we'll talk about enable better understanding of the nature tomorrow. So, I know I've said a lot, and there's a lot to change in the system, but I think the future of processing in memory is really bright. There are challenges in underlying technology, how to actually design these systems, but also overlying problems and requirements, which are really how do you adopt this. But by thinking across the stack, we can get a lot of benefits. This will come at a cost. So a lot of the time when you think about changing the model, it has to come at a cost, right? But we've seen examples of this cost before. And I'll go back to flash memory earlier. If there's one technology that's been very successful in the last 30 years in solid-state electronics or memory side, I believe that's flash memory, because flash memory has enabled these devices and many other devices that look like this. But if you look at this 30 years back, this was a very doubtful emerging technology. People didn't believe in it. People were writing NSF proposals on garbage collection flash memories, and they were getting rejected because what is this useless memory? But now flash memory has been enabled at cost. People paid the cost to enable it. As a result, we actually do a lot of things with it. But to enable it, we actually do a lot of things as well. There's actually a lot of infrastructure that goes into flash memory. Essentially, you have a processing system, which is the flash translation layer to make this work. Processing in memory is even harder, I think. You need to pay more cost. But maybe it's an idea whose time has come. But we need to be very careful with the adoption issues to make sure that we are able to use this technology in a widespread manner. Okay, that brings me to the end. I'd be happy to take more questions.
No questions? Okay, then, tomorrow at 2:30.
Okay.
Do you recall the room number?
Tomorrow is different?
Yes.
Okay, I don't recall the room number.
So there's a poster down in the lobby on the second floor which has the room number. And I'm not sure how to tell them how to find it any other way.
It's also online.
Is it?
If you go to the online announcement.
Sorry?
0.806.
0.806 in this building, okay? 0 point means it's down on the bottom floor. Good. Tomorrow at 2:30. Thank you.